problem. This is later slides, but this is okay. I think we can handle this problem now. Lottery. Okay, some of you have looked at this, and let's look at it all together if we haven't. Okay, lottery sells tickets with a 4-digit sequence. Okay, so the digits 0 through 9, 4 of them. And every Friday, a number is drawn, and if you match 4 out of 4, you win the grand prize. If you match 3 out of 4, then you win second prize. Okay, so what's the probability of winning each of those? Okay, so to set up a problem like this using the definitions that we have from probability, we have to define, as sort of just standard fare, we're going to define two sets. Okay, the set of all possible outcomes, that's sort of our sample space set, the universe of all possible things. If you want to talk about universes, that's basically the universe is a sample space. And then the event, okay, so that, we count them all up and we divide the two, and that gives us the probability. Okay, so just to make it clear what's going on here, a ticket is some sort of string of numbers, which I'm going to label A, B, C, D. It is ordered, okay, so it's not like Lotto Max where you can't have duplicated numbers. Okay, so that's more of a collection or a subset. We'll talk about those eventually, but that's not what's going on here. Okay, so 1, 2, 3, 4 is different than 4, 3, 2, 1. Okay, so the ordering of those things matters. Okay, so the way that we set up this problem is let's first define the sample space S. Okay, so this is all the possible draws. And we're going to let A be the set of all winning draws. And remember, we have bought a ticket, so there are, there's so many ways of matching this ticket, this ABCD up here. Okay. Now we're going to count those things, and we're going to count them using, basically the only counting formula that we have is this thing from last time where we have n distinguishable objects, and we're allowed to make some sort of sequence out of them, r of them, and it ends up scaling up multiplicatively n times n times n, r of those, so against the r times. Okay, so if we're asking ourselves what's the size of set S, you can think of it as there are and I sort of lay out the blanks here. Each blank has how many choices? 10, right? 0 through 9 has got 10 choices. And maybe it's obvious there's 10,000 tickets because you're used to doing arithmetic in base 10, okay? So maybe it is, but that's where it comes from, okay? So 10 to the 4 possible outcomes. All the winning outcomes, again, there are 4 blanks. What goes in the blanks? It's only one winning number, right? And if it's A, okay? If it's B, if it's C, if it's D, it's only one out of the 10 numbers that's going to match. And I know that seems a little trivial, multiplying by 1, but, 1 to the power of 4, okay, is still 1, right? So it's one chance in 10,000. Yeah. Okay, so just to finish off the problem. So the probability of a win is the size of A divided by the size of S, which is 1 over 10 to the 4, and that is something we can do in our heads. 1% would be 1 over 10 to the 2, divide that by 100, that's 0.01%. Okay, so not a large chance, but of course we want our grand prize to be something that is hard to win, right? Okay, probability of winning the second prize. You might have some instincts, you might have some, stuff from combinatorics you can use, but we're going to build on something else on other slides. We're going to come back to this and deal with it using some of the set stuff that's about to come. Okay, so we're going to put a pin in this for a moment. Okay, you probably have an answer at the ready, but we'll come back. Okay, let's just get a brief review from last time. Okay, so we're solving combinatorics problems, and that's going to be peppered in with all of the set stuff because we like to have a problem at the ready to deal with, some sort of theme, example theme for dealing with things. And this is it. Okay, so it's going to lead us to combinatorics eventually. There'll be a lot more problems when we get there. Things that you need to decide when you read a word problem, combinatorics-wise, does order matter? Okay, so ordered pairs, sequences, sequences of numbers on tickets, that sort of thing. Order does matter versus collections. Okay, so a collection would be, you just pick 4 out of the 10 numbers, and if you match all 4 in any order, that would be more of a subset type of thing. That would be this case down here. Order doesn't matter. Okay, so that would be more of a selection or combination. Are the objects distinguishable from each other? Okay, so all the digits, 0 to 9 are different, but it could be just the total of the digits that matters in some situations, not here, of course. And the last thing you need to pay attention to is, can you repeat things? Okay, in this case, you can repeat things. This is our first generalization. I'm going to write just a smidge more here because, permutation is the name of the game when it comes to these sorts of sequence type things. This one here with replacement, okay, so this is known as a permutation with replacement. In other words, you have the collection of numbers 0 through, so here that's what that means. So the with replacement, you have the numbers 0 through 9. Okay, so they're in a bag, you pull out a number, you put it in the first spot, and then the number goes back into the bag. Okay, so you can draw it again on the next round. Okay, so that's what is going on here, permutation with replacement. There are some where you're not allowed to duplicate things. That would be a permutation without replacement. Once it's out of the bag, it can't be repeated. Okay, anyway, the generalization is, and I use blanks as I put Oh boy. Anyway, yeah. So I use blanks. I put the number of possibilities in each of the blanks, and did I just get what happened there? It's like a train came in and ran us over, and then they just left. That was very strange. Did he leave something here? Was that you? Sorry, who Jack is? Wow, this is getting deeper and deeper. Okay, well, I got to find out more. All right. Anyway, I like using blanks. Sometimes people use boxes. Maybe you've seen boxes like in Mecca 101. Anyway, this is going to be a common theme when we get to combinatorics later. Okay, so a very nice technique. All right, let's get on to more set stuff. Yeah? Yeah. All right. Next order of business, the rule of sum. Okay, if you have a situation where A and B have no element in common, that is a disjoint set relationship. A disjoint set. A and B have no element in common. Here's our Venn diagram again, and this is the general Venn diagram for two sets. We can add something to this diagram to depict a disjoint set relationship. What should we add? Good, yeah, so the middle overlapping region here is empty. Okay, so here, mathematically, or algebraically, maybe it's better than mathematically, because there's many different ways of expressing math, but A intersect B, okay, so the intersect between them is empty, okay, so that is what disjoint means. If you like drawing general Venn diagrams from scratch, you might do this. You might just draw A over here and B over here, and they don't touch. Okay, so that might be another way of drawing it anyway. Okay, so, and tying this all into probability, which is what we would like, if A and B are events, their events, both events can't happen. Okay, so it's either one or the other, maybe neither, but both things can't happen at the same time. Okay, so that's the disjoint relation, and there is a rule that's associated with that. It's actually a theorem. If A and B are disjoint, then the size of A union B is equal to the size of A plus the size of B. Okay, we intend to prove this. Okay, it's going to be our first proof. And the way that we're going to do this is sort of, well, it's going to be an algebraic proof by cases. Okay, this bit here is going to be the left-hand side in our discussion. This one's going to be the right-hand side. And we're going to show that no matter where an element resides, it's going to contribute the exact same amount of stuff to the totals on each side. Proof. Suppose X is some element. We show by cases that X contributes the same to both sides. And by sides, I mean left-hand side and right-hand side. Okay, so what do I mean by cases? Well, X can be in several locations in this diagram. And case one, we're going to say, suppose X is in A. Okay, so if X is in A, we look at the left-hand side, and it contributes 1, like it's in A union B. So it contributes 1, plus 1, if you will, to the left-hand side. Okay? So X is in A union B, and adds 1 to the left-hand side. And if we look at the right-hand side, of course, there are two things, there are two sets. And it's got to contribute 1, a total of 1 to the total on the right-hand side. And clearly it's in A, so it's going to contribute 1. We got to make sure it doesn't contribute 2. Okay, so in other words, this thing should contribute 0. Why should this thing contribute 0? They're disjoint, and that means? Good, yeah, so it's in A, therefore it's not in B, because they're disjoint. Good. Okay, so X is not in B, because A and B are disjoint. So therefore A plus B adds, and I'll do it just under here, it adds 1 plus 0. Okay, so 1 plus 0 equals 1 to the right-hand side. Good? Good. All right, case 2. And the way proof by cases works is you try all the possible things, right? So it works out if X is in A. Let's see what happens if X is not in A. Well, if X is not in A, there's actually a couple possibilities. And just to show you what's happening on the diagram, X being in A means that it's here, right? So this would be case 1, is that X would be that dot in the diagram. X not in A, it can actually be in 2 different places, right? It can be in this region or this region. Okay? So it either can be in B or not in B. So there's actually going to be 2 subcases. Okay? So it's either in B or not in B. Yeah, no problem. Let's start off with not in B. Okay? So if X not in B, then how much does it contribute to each side? It'll be 0, right? Because it's not here, so that's 0, and it's not here, and it's not here. So 0 equals 0 plus 0, essentially. Okay, so then we contribute 0 to both sides. Sorry, sort of got a little hairy there. Okay, so that's, I guess, this region up here. So this is 2 part 1. And then 2 part 2 is x is in B. Okay, so x is in B. Then it's clearly in here. Okay, so that contributes 1. And this A contributes 0, and this B contributes 1. So it'll be 0 versus 0 plus 1. Okay, and, you know, I could write it out longhand, but I'm kind of running out of space, so we'll just, you know, we can see it. Okay, so contribute 1 to the left-hand side, 1 to the right-hand side, or 0 plus 1. Anyway, 1 to both sides. Okay, so we've done all the cases where to contribute 1 to both sides, 0 to both sides, or 1 to both sides. And so we contribute the same amount to both sides in all the cases. But. Okay, so this is, I mean, this takes some effort. We're not going to have to do this all the time. This turns out to be a very powerful rule, though. Okay, and we're going to apply this rule a lot of times, including to, yeah, some probability stuff, too. There's a probability rule that we'll get to in like a week or two. It's one of the axioms of probability. Says exactly this, but it divides through by s, okay, by the size of s, and it turns it into a probability. Okay, so it says that the probability of A union B equals the probability of A plus the probability of B whenever A and B are disjoint. Okay, so that is just an instant thing that falls out of it, plus some other good things, and we'll see how powerful this is when we do inclusion exclusion on the next slide. Okay, so far so good. Yeah. Okay, let's quickly go back to the opening slide. This is the thing that we needed to do the part B. Okay, so shall we go back and do that one? Okay. Now some of you might attack this thing with some combinatorics. You might say, well, there's 4 positions where you might differ, and then you multiply by 1 by 1 by 1. And that thing could differ in 9 ways. And that's a good combinatorial way of doing it. Now, we don't have all that yet. We will get there. But we can do it by disjoint cases, right? Okay, so we can break it up into cases that are easily countable, like these up here. Okay, and that's the way we're going to attack this today. All right, so let B be all the second place draws. Okay. Let me ask, what's the size of B? Well, if we consider what's in a second prize draw, right, there might be, if I can just draw blanks out here for a second, you know, it might be that we match the first 3, right? We match the first 3. We do that in, like, you know, one way. But the last one, we get wrong, right? And somebody just said 10. That's not quite right. How many ways can we get it wrong? 9 ways, yeah. Okay, so we don't want to get it right. We don't want to win the grand prize in this case. Okay, but that would be if you got the last digit wrong, right? And there are 4 different cases, right, where you end up getting a digit wrong. And I'm just going to list them out today. We could, you know, do this maybe a faster way, but this is fine for today. Okay, all of these sort of fit that 1119 pattern. Okay, where we got that one wrong, that one wrong, that one wrong. Okay, so what's in B? B is one of these 4 cases, and I'm going to say B is the union of B1, B2, B3, and B4, where B sub I is the case where we differ in the ith digit. Okay, all of these are disjoint, and maybe I could have added one more word in there. Okay, but I'll just circle this and say these are disjoint. Okay, so the rule of sum applies. Okay, so we can just add up all those cases. Okay, so the rule of sum applies. And each BI has a size of whatever it is, 1 times 9, 1 times 1 times 1 times 9. Okay, so the size of B is the size of B1 plus the size of B2 plus the size of B3 plus the size of B4, which is 9 plus 9 plus 9 plus 9, which is 36. And the probability of B is 36 over 10,000, which is a little bit better. It's still less than 1%, okay, 0.36% in this case. who said the lottery was easy to win, right? Okay, so just a quick way of breaking up cases. They're all the same case, so you could say, yeah, they're all the same case, 4 times 9. And we'll definitely do that sort of shortcut when the time comes. And we're going to do the rule of product a little bit later. Okay, questions about any of this so far? Okay, let's do inclusion-exclusion. Okay, we used inclusion-exclusion to solve that other problem the other day. Okay, so we sort of know what it is, that the overlap gets double counted. Okay, so the equality doesn't hold in general when the two sets are not disjoint. And the reason is, and I'll do maybe a better color addition this time, is if you add all the stuff that's in A, okay, the size of A, to all the stuff that's in B, yellow and blue make green, right? That green region was shaded twice. If you have issues with color, like I do, maybe you don't like this, right? So you sort of put tags or X's wherever you counted, right? So you counted all the stuff that's in those two regions, all the stuff that's in those two regions, and lo and behold, you see that the middle region is double counted. Okay, so why? Why doesn't this hold? Because the overlap, the elements in there, that's A intersect B, were counted twice. Okay, so the way to correct this is to use subtraction and take the size of the intersect. Hopefully the size of the intersect is as easy to count as it was when we did the nice numbers example. Okay, sometimes it isn't, so maybe this isn't practical, but we're going to use subtraction to fix it. Okay, so this is the theorem, the inclusion-exclusion theorem for two sets. Okay, we're going to prove it using the rule of sum, okay, which is really cool. All right, so what do we do? Okay, well, proof. We're going to start with A union B, and we're going to break it up into 2 bits. Okay, so the 2 bits we're going to break it up into are A and B minus A. Okay, so we're going to say that B minus A. So B minus A is this moon shape, just where the blue region is. So it's the moon, like with a bite taken out of the side, okay, like an old Apple logo or whatever. And if we union that with A, okay, we get the entire region. And you'll note that these two are disjoint. Okay, they don't overlap. Now we might do well to prove that. Okay, so we might want to verify. Okay, so let's just write down what we're gunning for here. So since A and B minus A are disjoint, okay, and we haven't proven that. Okay, and we might, as a formality, just actually go and prove that. Okay, so the size of A union B, we can use the rule of sum, on this thing. So is equal to the size of A plus the size of B minus A. Okay, and that's just by the rule of sum. Okay, very nice. Now, how would you verify that these two things are disjoint? How would you verify that the two things are actually equal to union? Okay, you might have to do some algebra for that. Okay, so I'm just going to put the proof on pause for a moment because the next slide actually shows you the algebra rules. Okay, and maybe it's time we did some of that. Okay, so just put that on pause for just a sec. Okay, so these are a refresh of what you did in Backup 101, and these are they match the laws of logic. Okay, so if you're doing logic stuff, but unions are ors and intersects are ands and complements are negations and whatever. They're the same rules if you liked one set versus the other, but we're dealing with sets, not logic. So this is it. This is the notation, and each of them has a name, and they also have a mate. I think they're called duals. Okay, so they're dual mate of the two, except for the double complement, which is its own dual. Anyway, most of these things follow what you can do in regular algebra. If union was something like a plus, and intersect was something like a times, and complement was something like a unary minus. Okay, something similar. There's some rules that don't exist. Okay, they're a little bit funny. I mean, this one is very clear, like A plus B is equal to B plus A. That makes sense. And you can multiply anything in whatever order that you want, as long as they're all the same operator. But you can't mix them. If you end up mixing them, you have to put brackets. Okay, and you end up having a distributive law. One of these should look familiar, right? Because you're used to distributing times through plus, right? Expanding brackets. You can expand brackets of plus through times, okay? So I put this here as this doesn't really exist in regular algebra as a highlighter. Same thing for De Morgan's law. This is distributing minus over a bracket. And the funny thing that happens is that the intersect becomes a union, and the union becomes an intersect when you do that expansion. Okay, so those are kind of funny. All these other ones are kind of normal. If you union A with itself, you get A back. You don't get 2A. Because you don't get duplicates in set land. And same thing, like there's no A squared. There's no number 2. Okay, so A intersecting with itself, you get the same thing back. That's idempotency. But A plus 0, you get A back. A times 1, you get A back. Okay, so that kind of makes sense. Those are identity laws. Multiply by 0, union with the universe, you get the universe, you get the empty set. And there's one other one that is included in MACM, but is not listed up here. Anyone remember what that was? Ooh, is that a long time ago? Is it too long ago? No, it's not too long. Never too long. No? Don't remember? Okay, I'll write it down for you. Maybe you can name the law. It's A intersect A union B. If you have that set up, this is actually equal to A. And similarly, it's dual, so A union A intersect B is A. Okay, which is a really juicy law because everything just sort of collapses down into one A. What's the name of this law? Absorption, good job. Anyway, I'm going to ask you to manipulate sets using this algebra set. So you're going to have to recall your skills in dealing with this. Most of the algebra is just like regular real-valued algebra with a few extra rules put in. Okay, and just to get us warmed up, we should do an example with one of these. Maybe let's, well, I don't have enough screen space to have both of these things appear. We're going to do an example. We'll do some algebra with these. So keep these handy, but I can't keep them handy for you because only one screen. Let's actually show that this is okay. Wrong color. So let's actually prove this. Okay. We should probably have proven it anyway, rather than say, yeah, this is disjoint, and these two things, this is actually equal as the union. Let's prove it. Yeah. Okay, so the normal way that we do this is we go step by step and do like right-hand side. Well, we do right-hand side from here because that's the more complex side. Okay, so let's just prove it up here. Okay, so let's write a proof. Okay, so the right-hand side of this is equal to A union B minus A. Okay. I will do the first step for you, but you guys as a group are going to do the rest. Okay. So the first thing that you should do, there's no rule that deals with minuses in the set algebra laws. Okay, so we would translate the minus out into something equivalent that uses just intersect and union and complement. Okay, so the substitution for B minus A is B intersected with A bar. Okay, and after some number of steps, we would like this to eventually equal the left-hand side, which is A union B. So you sort of know what the goal is. All right, over to you. What should we do next? Yeah. Okay, just you tell me what to write. Good. Okay, so I like to explain our steps as we go along, okay, and you should get in the habit of doing that too. Okay, so we use the distributive law there. Okay, it looks, well, worse in a way, but probably better. Okay, it got longer, but maybe that's okay. What's the next thing? A union A naught is the empty set, yeah. What's the law? What's the law? He's asking for help. What's that? It's not idempotent, someone help him out. It's the inverse law, good. And then? Oh, it's, you're right, sorry, it's S. Yes, you're right. So A union A bar with its, yeah, that gets the entire set. My fault for listening. Just copy what you did, thanks. All right. Okay, and then? Good. A union B, intersect S is just A union B. What's the law? Nope. Identity law, yeah. It's like multiplying by 1. That's an identity element. That's how you remember that. Anyway, that's the right. That's the left-hand side, so good. Okay. Okay, so that is just a little proof. Okay, 5 or 6 lines of algebra to prove our assertion that this actually works. And you can prove that they're disjoint. Okay, you would take A and B minus A and intersect them, right? Because that's what disjoint is, and see if it gives you the empty set. And it would pretty fast, right? The A and the A bar, if you rejig them around, they'll annihilate each other, and then that'll dominate out the rest. Okay. Anyway, you'll be asked to do stuff like this. Okay, so have some practice. Okay, but anyway. Yeah. Am I going to give you the laws when you're doing exams and quizzes? No. Well, yeah. I mean, it's algebra, right? Do you have to memorize them? Yeah, I guess you do. I guess you do. I know. It's, yeah, you gotta, you do algebra on a regular basis. It should be okay, right? It's not so difficult. All right. You're just complaining. All right, I get it. Okay. These are disjoint. So we have this. Cool. Okay, this is one step, though. Okay, there's another pair that are disjoint that we're going to do the same thing to. Okay, so what are the other pair? So it was A and B minus A. We're going to break up A into its 2 sets. No, wait a sec. No, we're going to break up B into its 2 sets. Sorry, we're going to break up B. Okay, so likewise, because we already have an A here. Okay, so likewise, B is the union of this set here. So that's A intersect B, union B minus A, and they're disjoint as well. And again, you can prove that. And I'm not going to do it here because I've actually made this an assignment problem for you on assignment 1. Okay? So you'll have a chance to do something similar to this, but it's for these two. Anyway, we apply the rule of sum to this. So the size of B equals the size of A intersect B plus the size of B minus A. And all we have to do is marry these two equations together. Okay, and we'll get the result. And some of you are already mentally doing that. I'm going to make it easy so that you see we rearrange this thing to be size of B minus A is equal to the size of B minus the size of A intersect B. Okay, and this bit will go in for this bit in here. Okay, and the result follows. Okay, so substituting for the size of B minus A, the result follows. Okay, and we usually substitute in the thing by bracketing it, but the brackets don't make really any difference. Okay, so a really clever way of using the rule of sum twice, okay, and just a little bit of sum algebra. We don't have to do anything complex. We don't have to do anything by cases. We could have done things by cases, but we don't have to. Okay, just pure algebra draws. Why are these two disjoint? Okay, well, if you look at where they are in the diagram, B minus A is just this blue region, and A intersect B is this green region. And you can see they don't overlap. Okay, that's my proof by picture. If you want to do the algebra, I mean, it's available to you on assignment 1. Okay, but it'll be something like this, right? Okay, other questions? Thanks for that. Other questions? Yeah, good? All right. Okay, can we do something similar for 3 sets? The answer is yes. And you probably saw this in Mac 101 as well, but in case you didn't, it's really kind of neat. And it extends to 4 sets and 5 sets and so on. There's a generalization. This is as far as we're going to go, but I'll explain how the generalization works. Okay, we're going to start by doing something similar. And rather than shade and put like lots of colors in here, I'm going to put X's in the diagram anytime that we use a region, anytime we count it. Okay, so similar to before, we start by taking the size of A and the size of B and the size of C and adding them all together. We are intentionally overcounting. We know this is not going to work. Okay, but let's just put X's in the regions that are counted. So that's all of A. This is all of B. And each of C's 4 regions gets an X. And you can see that some of the regions are counted exactly once, but all the regions in the middle are counted 2 or 3 times. So you can do something similar. Okay, so this is X's, and subtract off the single intersects. Okay, so you can subtract off, just like you did subtract off A intersect B and whatever, but there's going to be 3 overlaps. Okay, and what are the regions? A intersect B, A intersect C, and B intersect C. And to subtract these things off, what I'm going to do is I'm going to circle an X anytime we subtract it off. Okay, so we'll start off with A intersect B, so that X goes and that X goes. A intersect C, that X and that X goes. And B intersect C, that X and that X goes. And if you look at the gain state right now, it's almost there, right? Okay, so all the regions have exactly 1 X in them, except the middle region, okay, which is actually not counted. It's actually been undercounted by doing this. Okay, so everything's been counted. Except the middle region. So you add on the size of A intersect B intersect C, which I'll put in a different color, put the black X in there. Okay, so there's an X. Okay, so what did we learn from this? Well, we learned that we need a lot of information. Okay, we need 7 pieces of information, 7 overlapping regions to get the size that we want, whereas the previous one required only 3. And what's the information? It's all these regions that don't, intersect anything except themselves, minus all the single intersects. And then we add all the double intersects, and there's 1 of them. And does this generalize? It does. If you were to have like A, B, C, and D, if you have 4 sets, you would take, A, B, C, and D, you would add them all up. And then you'd subtract off all the single intersects, and there would be 6 of them. And then you would add all the double intersects back on, and there would be 4 of them. And then you would subtract off the triple intersects. Okay? And you keep on alternating the signs back and forth depending on how many intersects you have. But you need 15 pieces of information for that to work, and it scales exponentially. It keeps on doubling basically each time. So if you have 5 sets, you would need 31 pieces of information. 6 would need 63, and so on. Okay, but it does work, and it does generalize. but practically speaking, you're not going to do this for more than 3 things. Kind of neat, right? Yeah, like that. Some problems lend themselves really well to this this technique. You might see one on your homework. Okay, I think we have time for. We don't have time for the summary slide, probably. So we'll do set partition, and then we'll save the summary slide for the first thing on Monday. Okay, that'll be a nice review before we go into functions. All right. So last thing for today, set partition. And this is the last piece of terminology from the set part here. Okay. When A, B, and C partition S, each element of S is within exactly 1 of A, B, and C. Okay. So so we have a Venn diagram of sorts over here. Hopefully, a lot of you recognize this. What does this represent? StarCraft. Yeah. And there are 3 factions in StarCraft, 3 races. And if you ever watch tournament play, it's interesting. But everybody basically has the faction that they've mastered, right? So and so plays Zerg, so and so plays Terran, whatever. I think it would be a lot more interesting if you had to play random all the time, and you have to be a master of all the things. I think StarCraft would be a lot more interesting. But anyway, this is a partition essentially. The tournament world is a partition. Everybody pretty much plays in one of these sets, and not multiple of them. Okay, so this is a partition of the tournament world, and there are other partitions as well. Okay, what I'd like you to do is come up with algebraic relationships that represent a partition. So what is true for a partition? What do you think? They're all disjoint. Okay, what should I write? Good, yeah. So they're all pairwise disjoint. Okay, and the reason I asked you for clarification was because I didn't want you to say A intersect B intersect C was empty, which is definitely true, but it's not necessarily going to give you that they're pairwise disjoint. Okay, so good. I'm glad you came up with this. Okay, so pairwise disjoint. Okay, in the statistics world, when you have sets, multiple events, if you will, that no 2 of which can simultaneously occur, this disjointness is actually called mutual exclusion. And this can be pairwise mutually exclusive. Right? So no 2 things will intersect. Okay, this is certainly true so far. So nobody that's a Terran player will be a Zerg player, and so on. But this has not captured all of the things for a partition. What else do you need? Close. Yeah, we just need unions, not pluses. And that's equal to S. Good. Okay, so all of the elements, everything that's in the universe, has got to be in one of these 3 things. Okay, so if you have that, you have a partition. Okay, we're going to finish a minute early because, I don't know, it's probably right to do that. It's Friday. Let's get out, eh? Okay, so we'll see you on Monday, and we'll do the summary slide. This is actually an exercise, okay? So it'll be a nice review, and then we'll do functions. See you then.